Mr. Mukul Kumar, a first year BS student in Applied Artificial Intelligence from IIT Jodhpur. He will speak on thought provoking topic simulating early universe baryogenesis via quantum circuit, a new approach to matter antimatter asymmetry.
Hello everyone. The year was 1981 and Professor Richard Feynman uh, proposed a keynote. He was talking about uh, a physical computer following the laws of physics, and also he was talking about that computer uh, will be able to simulate nature. So, inspiring from that, I tried to simulate the events after the Big Bang. So, when the Big Bang occurred 13.8 billion years ago, the origin of universe exists, and there are two rules of matter, that when we create matter, antimatter also comes into existence. And there is a second rule: when when you when matter and antimatter meets, annihilation annihilation occurs, and they demolish each other, and all the matter and antimatter converted into the tremendous amount of energy. So here comes a question. Here comes a question: why we exist in today's universe? Because we are a form of matter. So to solve these mysteries, Professor Richard Feynman proposed that maybe antimatter moves backward in time, and so they never meet with antimatter never meet with matter to annihilate. But this proposal was illogical, I think, because now we have created antimatter at CERN labs and Fermi lab, and we have seen that matter does, doesn't move backward in time. But there are also many theoretical proposals, and grand unified theory, baryogenesis is, I think, one of the simplest and best proposal for explaining the asymmetry at the after the Big Bang. It talks about strong, weak nuclear forces and electromagnetic forces at the high energies, and at the X boson decay, the asymmetry happens due to the CP violation. So here is my setup for the experimentation. I I I have mapped the particles to the quantum circuit, and there at the first qubit you can see the X decay uh, representing the X boson, and followed by the quark at the second qubit, and anti-quark at the third qubit, lepton and anti-lepton. And after that, the main thing is that the magic happens at the qubit 1, where X boson decay creates a CP violation, which create the asymmetry. So after that, I created operators to interact these particles with each other to perform CP violation, and there you can see the final quantum circuit. At the first, you will see the qubits representing our particles, and followed by you can see some rotational gates representing the uh, operators which are which are making these particle interactions. And at the end you can see the measurement gates which are uh, which will give us a result. And this was a result. There you can see the quark count and anti-quark count. The quark count is exceeding, and you can see the matter you can see the matter percentage is 53 and antimatter percentage is 43. So 7.2 percentage uh, shows as a asymmetry, and we have successfully show the CP violation of baryon asymmetry. So uh, I have performed this experiment with a few qubits, but if we scale it further, we can see the huge amount of asymmetry, which conclude that after the Big Bang, when universe was exploding and br- getting broader and broader, the lot of asymmetry happens, and uh, the total amount of antimatter demolished, and this conclude that this tells us the reason why we exist today, because we are a form of matter. And if this doesn't happen, then there will be a antimatter version of ourselves, I think. So it is the conclusion you can read here, but I want to give my personal conclusion. That was we don't need a huge amount of money like billions of dollars to create actual particle accelerators or like CERN and Fermi labs. We can do it for freely if we have a quantum computer access, and we can simulate all these particle interaction events on the quantum computer itself to demonstrate the actual mm, particle physics. And also after this happens, there are so many things you can, then you can perform inflation dynamics and cosmic strings. And apart from that, even at the asymmetry, you can also perform CPT violation, and there you can see quantum gravity. And in quantum gravity, what you can do is that you can map the particles to the qubits, and you can apply some operational gates uh, uh, to apply the quantum gravity on those particles. Or you can map the objects, any kind of objects, to the those particles. And there is also a advanced attempt you can do. You can apply machine learning for the analyzing cosmic data. I will talk that about that later. So let me propose you a simple steps which you can perform in a better way. Experiments like this. The first step is to define what actually you want to uh, simulate on the quantum circuits. And after that, the art is of mapping those problems on the quantum circuit. Few weeks ago, I tried to simulate human brain to these these quantum circuits. What I did, that I mapped the neurons to the qubits, and I tried to I was researching about how human brain works. So uh, I understand that human brain learns about things after making connections of neurons. So when I map neurons to the quantum circuit, I make connections through the entanglement. And then I also try to add some operators to uh, make sharing of those liquids like dopamine, but those are complex molecules. And I think I have a lack of knowledge about how human brain works. So I stuck there at those operators of simulating those molecules like dopamine and other chemical molecules. They are too much complex. Even quantum circuits couldn't handle them. Even yes, now I want to talk about the actual thing, quantum neural networks. This is a kind of quantum intelligence, and here what we can do is that we can create a neural network which can perform this experiment in loops and learn about these things by itself. And what it can do is, like, in this circuit, the experiment can be run in the loop, and this quantum intelligence uh, can analyze these can analyze these gates, and by itself and again that intelligence can change these parameters and get different result and learn about them. So by doing this, the intelligence can be conscious about the entanglement properties and superpositions. It's just like somebody is experiencing that experiencing the quantum mechanics and roaming in the quantum realm. So that's all for my side. You are welcome to ask questions.
Thank you for your presentation.
Okay, thanks.
I have a few comments to make.
Okay.
It is not correct to say that Feynman said particles moving backwards in time are antiparticles.
Yes.
No physical particle can travel backwards in time, even in Feynman's scheme. Only states with negative energy, which are otherwise unobservable, only they can be interpreted as antiparticles traveling backwards in time.
Yeah, I
It's
have
very
said that.
important because no positive energy state can travel backwards.
Yeah, I have said that that was illogical.
No, you said it in a somewhat
Yeah, I
incoherent
mentioned
manner.
that because it's
You
kind of
mentioned the negative energy states, but your first statement was that particles traveling backwards in time.
yeah.
No, that is an unacceptable statement.
Yeah. I have mentioned that that was a illogical attempt created by Richard Feynman. I found this funny, so I mentioned it here. And
And
I know.
secondly, your fundamental assumption is the universe begins with no asymmetry. And this is an untestable assumption.
Yeah.
It may seem very reasonable, but there is really no way of checking that.
Yeah, that's why we are performing this experiment to see what happens
So it
actually
involves
at
a
that
lot
point.
of assumptions. Therefore, we don't
Yeah.
know whether the current observed asymmetry is such that initial asymmetry was zero and it developed later due to particle physics.
Yeah, you're right.
My third point is a bit of an objection actually, is that you are dealing with a finite temperature universe. You cannot use pure states of quantum theory. You cannot use vectors in the Hilbert space. You have to use density matrices, which are mixed states, and in particular, you have to use mixed states that are thermal. So I don't know what to make of this simulation that you have done in terms of pure states.
Actually, I'm not an academic person. I just do these experiments for my fun activities, and I'm just a kid. I'm just doing these all these things for exploring. But you mentioned these kind of things. I learn about them. I try to apply those
So
days.
of course, it's an interesting question whether quantum simulations can be adapted to density matrices. How to do that, I don't know, but
But I will
maybe a
try
way of
it.
doing that.
Maybe I will successful at it. Even before performing this experiment, I don't imagine. I don't think that I will be able to do that. Also, I think it was impossible. But when I started learning about these things and doing this simulation step by step, I concluded with this final. But I know that you have mentioned that there are also a lot of things to consider, like temperature and all this. I will try also to apply to these circuits.
Thank you.
Thank you very much, sir.
So, could you give more detail about your simulation setup? And I think there are few earlier works on this area. Could you give a summary of that?
So simulation setup. So I have used toolkit, IBM's software toolkit known as Cascade, and I have used that cascade just to use quantum hardware and but apart from all these operators and all these things, I have to develop by myself because that toolkit have its own limitation. That toolkit was just built to use quantum computers. So uh, the experiment the 50% of experiment is built by with built by me only, and I have used Python, and I'll say you my work if you are interested. Whoever asked this question.
One more question. You said that matter dominated antimatter, and that's why asymmetry happened. But why is that? And as we know, when matter and antimatter interact, they both get annihilated. But then why this much matter survived? And don't you think spin conservation is getting violated with this?
So matter dominated antimatter. I think there I mentioned at the slide there is a parameter mentioned epsilon. So I want to say that if epsilon is equals to zero, then that means that matter and antimatter they have collapsed themselves and create nothing. So nothing exists. Everything has been converted into energy. If epsilon is below the zero, then their antimatter will dominate and defeated the matter. And uh, if beyond zero, then matter will dominate the universe, and antimatter will be defeated. And when I saw the experiment there, you can notice the asymmetry was point 1, I think. And if that means that asymmetry is 0.1, that means matter is dominating the antimatter.
I'd like to make a small comment on experimentation versus simulation. As you said, what's the need of building particle colliders if we can just simulate? But my point is, when you're running a simulation, you cannot know the initial states of the particles. We don't know everything, the initial conditions. But when we're doing experiments with particles already in the universe, then I think we come around that problem. I think there's a reason like so much money is spent on particle colliders. So what do you think? Like, can experiments be fully replaced by just simulations? Plus, as Professor Haridas also mentioned, like there is this thing about the pure quantum state problem as well.
Yeah, all these things matters on the quantum hardware. We have not very much qubits.
No, but even quantum hardware, or even if you talk about quantum computing with less noise, even that is very expensive, right? So
Yeah, that is also expensive, but still, uh, I mentioned about those particle accelerators just because, uh, like in India, if you want to do that kind of research, we have a lack of funding. So that doesn't mean you stop working on that. You search for alternative ways, and this is kind of a jugaad, we can say. And at jugaad, you can't expect the perfect things.
okay, got
Okay,
it,
let it go.
got it.